So in number 47, we have a hypodermic syringe containing a medicine with a density of water. The barrel has a cross-sectional area of that. In the absence of a force in the plunger, the pressure everywhere is 1 atmosphere. A force now is applied, 2 newtons is applied to the plunger, making the medicine squirt from the needle. Determine the medicine's flow speed through the needle. Assume the pressure in the needle remains at 1 atmosphere and the syringe is horizontal. All right, so we're using Bernoulli's equation in this case. Here's the full form of it. One quick note, because it's horizontal, we know that the height here is going to be equal to the height here, so we can immediately ignore those two terms. Now, the tricky part, what's the pressure? Well, they tell us that the pressure everywhere is 1 atmosphere before the plunger is pushed. By pushing on the plunger with a force of 2 newtons, we increase the pressure at P1 more now than P2. How much more? Well, we can use the definition of pressure, which is just force over area. So that 2 newtons divided by the area of the plunger will give us the additional pressure that's exerting in this area here. So solving this. So atmospheric pressure, College Board uses 10 to the 5th, so I'm using that. So the pressure in the needle is still 10 to the 5th, but in the plunger area, the pressure is now increased by that 2 newtons divided by the area, 2.5 times 10 to the minus 5th. If we solve that, we'll discover that the additional pressure is 80,000 pascals. We can subtract the 10 to the 5th, the atmospheric pressure from both sides of this one, and that gives us just the additional pressure on the plunger side is 80,000. Now, one little trick on this one. We assume that the needle is much, much smaller than the area of the plunger area here. And so we're going to make an assumption, and this is the one that usually trips students up on this one. They're like, well, we don't know what the velocity of the medicine is in the plunger area. Well, we're going to assume it's very, very small. Typically, we're going to just say it's about 0. And you might get arguments with that one, but normally think about the needle is much, much smaller diameter than the rest of the plunger area. If we do that, we can eliminate that term, and we simply end up with this. 80,000 equals 1/2 the density times V2 squared. Density, again, is that of water, 1,000. Simplifying it down, dividing both sides by 500, we get 160 equals V2 squared. And if you take the square root of that, we'll discover that V2 is about 12.6 meters per second. This assumption right here is the one that traps students and people like, oh, wait, we can't actually solve this problem because we don't know that. Yeah, that one's a little tricky. Good luck. Have a good night.